previous lectures, we have studied about deadlock prevention and deadlock avoidance. In the previous lectures, we have studied about deadlock prevention and deadlock avoidance, and we have seen various methods and algorithms that we use for preventing and avoiding deadlocks. So now, think of a system that does not employ either of deadlock prevention nor deadlock avoidance. In the previous lectures, we have studied about deadlock prevention and deadlock avoidance, and we have seen various methods and algorithms that we use for preventing and avoiding deadlocks. So now, think of a system that does not employ either of deadlock prevention nor deadlock avoidance. So what will happen in a system like that? So in a system like that, there is a high chance that a deadlock could occur because it does not have any mechanisms for preventing nor avoiding deadlocks. So in such a system, it is a must that it should have a deadlock detection algorithm. That means it must have a method to detect that a deadlock has occurred, and if a deadlock has occurred, we should have some mechanisms to recover from that deadlock. So in this lecture, we are going to study about deadlock detection. So this is actually a costly solution because we know that prevention is always better than cure. So instead of allowing deadlocks to occur in the first place, if we can try to prevent or avoid it before happening, then that is the best. But there may be systems which does not employ any methods for deadlock prevention nor avoidance. So in that cases, we need the deadlock detection. So here we are going to study about deadlock detection, and later on we will be seeing the methods for recovering from a deadlock once the deadlock is detected. And again, we have seen that there are two types of systems that we have been discussing. Systems where the resources have a single instance of each resource type, and there are systems where the resources have multiple instances of each resource type. So in this lecture, we are going to study about deadlock detection for systems where there is a single instance of each resource type. So let's see how we can detect deadlocks in this kind of systems. So here, in systems where each resources have only a single instance, we can use a wait for graph, which is an algorithm for deadlock detection and is a variant of the resource allocation graph which we have studied earlier. So in order to detect deadlocks in systems where there are only single instances of each resource type, we are going to use an algorithm called the wait for graph. So this is an algorithm and it is used for detecting deadlocks, and it is a variant of the resource allocation graph that we have studied earlier. So we have already discussed about resource allocation graph, and we have explained how resource allocation graphs are designed and how we are able to know if there is a deadlock by looking at the resource allocation graph. So we said that when there is a cycle in the resource allocation graph, it means that there could be a deadlock. So now we are going to use the wait for graph, and let's see how is this wait for graph different from the resource allocation graph. So we obtain this graph from the resource allocation graph by removing the resource nodes and collapsing the appropriate edges. So in resource allocation graph, we know that we had nodes for processes and resources. So the circles represents the processes, and the rectangles or squares, they represent the resources, and the corresponding edges were there. But in this wait for graph, what we are going to do is we are going to remove the resource nodes. That means those squares or rectangles will be removed, and we will be collapsing the appropriate edges. That means we'll be removing the edges that corresponds to that, and then we'll be forming a graph with only processes. We'll see how it is done as we move ahead. So in a wait for graph, an edge from process Pi to process Pj indicates that process Pi is waiting for process Pj to release a resource that is needed by Pi. So in a wait for graph, if you see an edge, that means an arrow pointing from process Pi to Pj, then what does it mean? It means that the process Pi is waiting for Pj. And why is it waiting for Pj? Because Pj is actually holding some resource which is actually needed by Pi. So Pi wants to use some resource, but that resource is currently being held by Pj. So Pi is waiting for Pj to release that resource so that it can get hold of that resource. So when you see an edge or arrow from Pi to Pj, that means Pi is waiting for Pj to release the resource that Pi wants to use. So the same thing, if we depict in terms of a resource allocation graph, it would look something like this. So let's say that the resource that PI wants to use is called RK, and then that RK is currently being held by the other process, which is PJ. So in the resource allocation graph, we will be depicting it like this. PI wants RK. So there is an arrow or a edge going from PI to RK, but the resource RK is being held by PJ. There is an arrow going from RK to PJ because RK is currently being held by PJ. So this is how it looks like in a resource allocation graph. So when we convert it to a wait for graph, we are removing the resource nodes and we are collapsing the edges. So what happens? From here we see that PI is waiting for PJ. So we are removing this RK from here and we are putting an arrow right from PI to PJ. So PI to PJ. So that is what it will look like in a wait for graph. So from the name itself, it is easy to understand that wait for graph means it shows the processes that is waiting for another process to release a resource. Alright, so now let's see how we can depict this graphically by drawing the graphs. So first of all, here we have a typical resource allocation graph, which is similar to the resource allocation graphs that we have already discussed. So let's see and analyze this resource allocation graph that we have. So here we have 5 processes, P1, P2, P3, P4 and P5, and we also have 5 resources, R1, R2, R3, R4 and R5. So if you look at here, let's start from process P1. P1 actually wants to use resource R1. So there is an arrow going from P1 to R1 because it wants to use R1. But R1 is currently being held by P2. The arrow from R1 is going to P2. That means R1 is currently being held by P2. Similarly, P2 wants to use resource R3, but R3 is currently being held by P5. Also, P2 wants to use resource R4, which is currently being held by P3. And P2 also wants to use R5, which is also held by P4. And if you look at P3, P3 actually needs R5, but R5 is held by P4. And if you look at P4, P4 wants to use R2, but R2 is currently being held by P1. So this is a resource allocation graph. So we see that in resource allocation graph, if there is a cycle, we said that there could be a deadlock. Alright, now let us make the corresponding wait for graph using this resource allocation graph. So this is how the corresponding wait for graph will look like. So if you see here, we have eliminated all the resource nodes. The rectangles or the squares are now gone and we only have the processes. So in wait for graph, we are only going to have the processes or the circles. So now let's see. So let's start from P1. So P1, as we said, it is waiting for resource R1, which is being held by P2. So we see that P1 is waiting for P2 to release the resource R1 so that it can make use of R1. So P1 is actually waiting for the process P2. So that is why we have an arrow from P1 to P2. So P1 is waiting for P2. Now if you look at P2, P2 actually wants to use the resource R3, but R3 is held by P5. So P2 is waiting for P5 to release the resource R3 so that it can use it. So if you look at P2, there is an arrow going from P2 to P5 because P2 is waiting for P5 to release the resource that P2 needs. Alright, similarly, P2 also needs the resource R4, which is currently being held by P3. So P2 is also waiting for P3 to release R4. So that is why there is an arrow from P2 to P3. And similarly, P2 is also waiting for P4 to release R5. We see that P2 wants to use R5, but it is being held by P4. So P2 is also waiting for P4 to release R5. So that is why there is an arrow from P2 to P4. So those are the things that P2 is waiting for. P2 is waiting for P3, P4 and P5. Okay, now let's look at P3. P3 is actually needing resource R5. It is waiting for R5, but R5 is being held by P4. So P3 is actually waiting for P4 to release R5. So there is an arrow from P3 to P4. And if you look at P4 here, P4 actually wants to use R2, but it is being held by P1. So P4 actually is waiting for P1 to release R2. So there is an arrow from P4 going to P1. So we see that P4 is waiting for P1. So this is the corresponding wait for graph. So we have removed the resource nodes and we show directly how the processes are waiting for each other. So this is the corresponding wait for graph. Now how do we know that there is a deadlock here? So similar like the resource allocation graph, even in the wait for graph, a deadlock exists in the system if and only if the wait for graph contains a cycle. So if there is a cycle in a wait for graph, that means there could be a deadlock. So if you look at here, P1, P2, P4, P1, there is a cycle here. Also P1, P2, P3, P4, P1, there is a cycle here as well. So there are many cycles if you check again in this corresponding wait for graph. So if there is a cycle in the wait for graph, then we can say that there is a deadlock detected in the system. So this is how we can detect deadlocks using a wait for graph. So when we use resource allocation graphs in the previous algorithms, we were using it for avoiding and preventing deadlocks. But here the wait for graph is being used for detecting the deadlock. So we'll have a wait for graph which should be formed after some regular intervals of time in the system, and it should always check if there is a cycle being formed or not. So if there is a cycle in the wait for graph, that means that there could be a deadlock in that system. So this is how we detect deadlocks in systems where there are only a single instance of each resource type. So as I already told you, this wait for graph method can be used only for systems where there is a single instance of resources. But if there are multiple instances of each resources, this wait for graph will not work. So for that we'll need to use some other algorithm which we'll be discussing in the next lecture. So I hope this was clear to you about how to detect deadlocks in systems where there is only a single instance of each resource types. So I hope this is clear to you. Thank you for watching and see you in the next one. In this lecture, we are going to discuss about deadlock detection in systems where there are multiple instances of each resource type. So we saw that the previous algorithm, that is the wait for graph which we have discussed in the previous lecture, could be used only for systems where there are single instances of each resource type. So for systems where there are multiple instances of each resource type, we need a different algorithm. So that is what we are going to discuss here now. So here this algorithm, it employs several time varying data structures that are similar to those used in the banker's algorithm. So if you remember, the banker's algorithm was something we used for avoiding deadlocks in systems where there are multiple instances of each resource types. So similar to the banker's algorithm, even in this algorithm, we are going to use some time varying data structures, and it is somewhat going to be similar to the banker's algorithm. So let us see what are those data structures that we need to use for using this algorithm. So first of all, we have a data structure called available. It is a vector of length m indicating the number of available resources of each type. So this available is a vector of length m, and it will denote what are the number of available resources of each type. So it is somewhat similar to the banker's algorithm that we have already discussed. Now let's see what is the next one. So the next one is allocation. It is an n by m matrix which defines the number of resources of each type currently allocated to each process. So this is also somehow similar to the banker's algorithm, and from the name itself it is easy to understand. Allocation means we are trying to say how many resources of each type are allocated to each process. So it is a n by m matrix. So n denotes the number of processes and m denotes the number of resources. So it will denote how many number of each resource type is allocated currently to each of the processes. So that is what we mean by the allocation. So the next one that we have is the data structure called request. So what is this? It is an n by m matrix that indicates the current request of each processes. So again, n is the number of processes and m is the number of resources, and request is a matrix that indicates what is the current request of each process. So each process, what are the current requests that they are making? That is what we mean by request. So it is denoted like this. If request of ij equal to k, that means process pi is requesting k more instances of resource type rj. So request of ij equal to k. So I is the process, j is the resource, and k is the number it is requesting. So request ij equal to k means the process pi wants k more instances of resource type rj. So if we take a number, let's say k is equal to 3. So that means process Pi wants 3 more instances of resource type Rj. So that is what we mean by the request. So this is also similar to the banker's algorithm. Alright, now let's go to the algorithm and see how this algorithm is working. So coming to the algorithm, we are going to use two vectors again, which is work and finish. So let work and finish be vectors of length m and n respectively. So remember that m is the number of resources and n is the number of processes. So work is a vector of length m and finish is a vector of length n. Alright, so now we are going to initialize work is equal to available. So what is available? Available is the number of resource instances available at the particular point of time. So whatever is available, that same value we are going to put inside the vector work. So work is equal to available. Now, if allocation is not equal to 0, then finish of I is equal to false. Else, finish of I is equal to true. For I equal to 0 up to n minus 1. That means for all the processes. Now what do we mean by this? If allocation is not equal to 0. So what was allocation? Allocation is the number of resource instances that is allocated to the processes. Now if allocation is not equal to 0, then finish of I is equal to false. Now finish of I is something that is used to denote if the process has finished its execution or not. So if finish of a particular process I is equal to false means the process has not finished the execution. And if finish of I is equal to true for some process, then that means that particular process has finished its execution. So when allocation is not equal to 0, that means when there is something allocated to the processes, that means the finish is equal to false. That means the process has not finished the execution. So we know that when a process has finished its execution, it is going to release all the resources that were allocated to it. So when a process has actually finished execution, then the allocation will be equal to 0 when the process has finished execution. So what we mean by this is, if allocation is not equal to 0, so if this is a bit confusing, let's go in the other way. So let's say if allocation equal to 0, so if it is equal to 0, then what happens? That means there is nothing allocated. And if there is nothing allocated, it means the process has completed its execution. So that is why we will be seeing this else part, finish of I equal to true. But if allocation is not equal to 0, that means there is still some resources that is allocated to the process. That means it has not completed its execution. So finish of I will be equal to false. So when allocation is not equal to 0, that means finish is false. And if allocation is equal to 0, that means finish is equal to true. So that is what we mean by this. If you just analyze it carefully, you will not be confused. Alright, so that is the initialization part. So coming to the next step, find an I such that both finish of I equal to false and request of I is less than or equal to work. So we are going to find a process such that finish is equal to false. That means it has not finished its execution yet. And also the request of I, that means the number of resources that the process is requesting is less than or equal to work. And what is work? In work we have the value of available. That means the available resources. So if the request that the process is making is less than or equal to the available, then that means we can satisfy that request. But if the request is greater than the work, that means if it is greater than whatever resources is available, then we cannot grant that request. Alright, so if we find an I such that both finish of I is equal to false, that means the process has not finished execution, and also the request that it is making is less than or equal to work, then we can go to the next step, which is step 3, where we allow that process to complete its execution, and after it completes its execution, it has to release the resources that it was allocated. So the new work will now become the old work plus whatever was being held by Pi, and it has now released. So that is now the new work. And then we've set finish of I is equal to true, which means that that particular process has completed its execution. And then go to step 2. So we go to step 2 again to find the next which can execute if it is following these two conditions. Now what happens if this condition becomes false? That means we are not able to find an I such that finish of I equal to false and request of I is less than or equal to work. So what will happen? So there are two cases here. So the first one is if the second condition, that is request of I is less than or equal to work, fails. That means if the request of I, the request that is made by process Pi, is actually greater than work. That means it is greater than the number of available resources that we have at that particular instance. Then we cannot allow that process to do its execution. So that is one case where it can fail. And another case is when finish of I is actually true. So finish of I is true means that process has actually finished its execution and we don't need to bother about that. So after coming to the step 2 and step 3, and it keeps iterating within the step 2 and step 3, and a time comes when we are not able to find any I which is satisfying these two conditions, then we go to step 4. So in step 4 it says that if finish of I is equal to false for some I, then the system is in a deadlocked state. And we can particularly say that it is Pi, or the process Pi, that is deadlocked. So for all the processes which are there from 0 to n-1, step 2 will work. So it is going to check if there is any process where we are able to satisfy the request. And if the request is being satisfied, it will go to step 3, and then it will again come back to step 2. And again it will check, is there any other process whose request can be satisfied. If there is, it will be satisfied in step 3 and we'll go to step 2. So this will keep happening. And if a time comes when there is no processes whose request can be satisfied, and still there are some processes which has not completed its execution, that means we are in a deadlock state. That means the process is making a request, but we don't have available resources to meet that request. And the process also has not completed its execution. And we are not able to move further. How many ever times we iterate between step 2 and step 3, we are not able to find any process whose current need can be satisfied with the current number of resources that we have. So at that point, it will just go into that loop. It will just try to wait for resources to become available, but it is not going to be available and it is going to be in a deadlock state. So that is what we mean in step 4. That means there is at least one process that has not finished its execution and we are not able to satisfy the request, then the system is in a deadlock state. So that particular process that leads us to step 4, that is process I, that ith process is the one that is deadlocked, and that makes the system in a deadlocked condition. So this is the algorithm that we can use for detecting deadlocks in case we are having multiple instances of each resource types. So it is somewhat similar to the Banger's algorithm, but in Banger's algorithm we are trying to avoid the deadlocks. So there is one more algorithm which we have discussed in Banger's algorithm, the sub-algorithm, which is used for making sure that the system is in a safe state. But here we are not bothered about that. We just want to see if the system is in a deadlock state or not. So using this algorithm, we can find out whether the system is in a deadlock state or not. So this was the algorithm, and in the next lecture we will be taking an illustrative example and we will see how this algorithm works in that example. So I hope this was clear to you. Thank you for watching and see you in the next one. In the previous lecture, we have discussed an algorithm for deadlock detection in systems where there are multiple instances of each resource type. So in this lecture, we are going to take an example and see how to apply that algorithm in this example. So if you have not watched that lecture, I recommend that you would watch it first and then come to this example, because it is that algorithm that we are going to apply in this example. Alright, so let's get started. So here, consider a system with 5 processes, P0 to P4, and 3 resources of type A, B, and C. And resource A has 7 instances, resource type B has 2 instances, and type C has 6 instances. So this is the example that we are going to discuss. We are having 5 processes here, and then there are 3 resources whose instances we have mentioned here, A7, B2, and C6. So suppose at time T0, the following snapshot of the system has been taken. So this is the snapshot of the system at some point of time T0. So if you look here, we have the processes P0 to P4, and this is the allocation, which denotes the number of instances of each resource type that is allocated to the processes at the current time. So for P0, there are 0 instances of resource type A allocated, and for P0, there is 1 instance of resource type B allocated, and for P0, there is again 0 instances of resource type C allocated. And similarly, we can see the others for processes P1 to P4. And the next one is the request. That means the current request that the processes are making, how many more resources it is needing to complete its execution. So if you look at process P0, it is requesting 0, 0, 0 of all the types of resources A, B, and C. That means it does not need any more resources of types A, B, or C. So it is actually satisfied with this allocation and it can complete its execution. For process P1, it needs 2 more instances of resource type A, so that is what it is requesting, and it needs nothing from resource type B, and it needs 2 more instances of resource type C. So this is the request from process P1. And similarly, we can see the other requests from processes P2, P3, and P4. And then the available. So what are the remaining resources that are available? So here it shows 0, 0, 0. So why is it 0? If you look at the allocation, these many resources are already being held by these processes. Currently they are being held. So let's see. Resource type A. So here we see that process P0 is not having any. P1 is having 2, P2 is having 3, P3 is having 2, and P4 is not having any. So if you just add up these resources of type A, we see 2 plus 3, 5, 5 plus 2, 7. So 7 instances of resource type A is currently being held by the processes. And if you see, we are having a total of only 7 instances of resource type A, and all the 7 are being held here. So that is why there is nothing available now. The availability of resource type A is 0. So similarly for B also, if you see, if you add up 1 plus 1, 2. And how many do we have? We have only a total of 2. That is why B is also 0 available. And if you look at C, 3 plus 1 plus 2, which is 6. So we only have 6 instances and all the 6 are allocated. So there is nothing available of C as well. So this is the current snapshot of the system at some point of time T0. Alright, now let us see if this system will go into a deadlock, or if there is a safe sequence that can be there to prevent deadlock from happening. So let's see. So when we discuss the banker's algorithms example, I have taken the snapshot of each of the iterations of the algorithm and shown how it works. So I'm not going to repeat the same thing. So here what I am going to say is that there is a safe sequence. Alright, there is a safe sequence in this system. So first of all, I will show you the safe sequence and I will show you why that is a safe sequence. I'll not take the snapshot of each and every iterations again. So let's first see what is the safe sequence and how did we arrive at that. So if you execute our algorithm that we discussed in the previous lecture, we see that we will get a safe sequence in this form. P0, P2, P3, P1 and P4. So if we follow in this sequence, we will be able to satisfy the needs of all the processes and they will be able to complete their execution without leading to a deadlock. So remember that how this works is using the algorithm that we discussed. So it is going to check for all the processes from P0 to P4, and whichever process needs to wait will wait, and whichever processes whose needs can be satisfied will be satisfied, and will be going on like that. And the processes that completes their execution will be releasing the resources. So hence our available number will increase, and it will again check for the processes that has not completed execution, and it will try to see if there is a safe sequence that can be formed by iterating through that algorithm again and again, and find if we can actually satisfy the needs of all the processes and complete the execution. So that is what it's going to try. But if it gets stuck somewhere, that means there is a deadlock. But if it is able to satisfy the needs of the processes in some or the other order, then that means there is no deadlock. So here I am saying that there is no deadlock because we have a safe sequence here. So let us see how the safe sequence is formed. So starting from process P0. Now, why are we starting from P0? We see that P0 does not need any of the resources anymore. It does not need A, B or C. The request is 0. So whatever P0 is having, that means the allocation of P0, with that itself it is able to complete its execution. So that is why we are starting with process P0. So now let us see what is the available resources here. So I'll take another table here to keep a track of the available count at each instance of time. Okay, so this table will show the number of available resources of each type at particular instances of time as we move ahead. Okay, so as I said, we'll start with P0. So right now the available resources are 0, 0, 0. Now P0 will execute. Now P0, as I said, does not need any of the resources anymore. It is happy with what it has. So it will use the resources that is allocated to it, 0, 1, 0, and it will complete its execution. Now when P0 completes its execution, we saw that P0 was holding one instance of resource type B and nothing from A or C. Now when it completes its execution, it will release this instance of B that it was holding. So our available count will now increase. So our new available is 0, 1, 0. There are nothing from resource types A and C, but there is one instance of B available now because P0 completed its execution and it released the B that it was holding. Alright, now let's see what is the next process that we can execute. Now if you look at this request table, we see that P2 also does not need any extra resources. The request from P2 is also 0, 0, 0. So we can definitely satisfy the need of P2 and we can allow its execution. So now P2 will execute, and it was holding 3 instances of A, 0 from B, and 3 instances of resource type C. So P2 will execute, and after P2 executes, it will release the resources that it was holding. So that will again increase our available count. So this is our new available count now. There are 3 instances of A released by P2. So now it becomes 3. And this one, which is the previous instance of B that was released by P0, that is the same here. And then there are again 3 instances of resource type C that was released by P2. So that is the 3 that is mentioned here. So now our new available is 3, 1, 3. So these many resources are available. So with these many resources, let's see what is the next process that we can satisfy. Now if you look at here, P2 needs one instance of A. And do we have one instance of A? Yes, we are having actually 3 instances of A. So this can be satisfied. And it does not need anything from B or C. So definitely we can satisfy the need of process P3. So we will allow P3 to execute. And after P3 executes, it is going to release the resources that it was holding, which is 2 instances of A, 1 instance of B, and 1 instance of C. So let's say P3 has completed its execution, and so this becomes our new available. So why is it like this? So there were already 3, 1, 3 which was available. So P3 released 2 instances of A. So this 2 plus the previous 3. So 3 plus 2, 5. And then it released 1 instance of B. So there was already 1 available. So 1 plus this 1, 2. And then there was already 3 instances of C available. And then P3 just released 1 more. So 1 plus this 3 becomes 4. So the new available becomes 5 to 4 after P3 completes its execution. Okay, so now we have 5 to 4 available resources of resources type A, B and C respectively. Now let's see which is the next process that we can satisfy. So if you look here, P1. So P1 needs 2 instances of A. Do we have that? Yes, definitely we have. We have 5 actually. And it needs 0 instances of B, and it needs 2 instances of C. Do we have 2 instances of C available? Yes, we have. We have 4 actually. We have more than what it needs. So we can satisfy the need of P1. Actually, P4 also can be satisfied. So we can go with either P1 or P4. So let's go with P1. So let's say P1 is now allowed to execute, and after it executes, P1 is going to release the resources that it was holding. So how many resources were P1 allocated? It was having 2 instances of A and nothing from B and C. So our new available becomes 724. Why? Because there were 5 instances of A already available, and P1 after executing is releasing 2 instances. So 5 plus 2, 7. So 7 instances of A is now available, and then this B and C, it is the same 2 and 4, because there was nothing held by P1 from B and C. So now we are having 7 to 4 resources available. And the last process that we have is process P4, and P4 needs how many? It just needs 2 instances of C, and we already have 4 instances of C available. So we can definitely satisfy the request of P4 also. So P4 also will be allowed to execute, and once P4 completes its execution, the new available will be 7 to 6, because we see that P4 was holding nothing from A and B but 2 instances of C. So once it released these 2 instances of C, if we add that 2 with the previous 4 which was available, it becomes the 6. So 7 to 6. So this is the final available. And we see all the processes have completed their execution. And the order was P0, P2, P3, P1, P4. You may be able to find other order as well, but the point here is that we were able to satisfy the needs of all the processes in some order, and it did not lead to a deadlock. So if you look here now, A has 7 instances, B has 2, and C has 6. 7 to 6. Everything is being released now. So this is the available number of resources now. And there is nothing allocated now, because all the processes have finished their execution. So when they finish, they will be releasing it. So that means finish of I is equal to true for all the processes, and hence there is no deadlock in this system. Alright, so this is how we can apply that algorithm and find out if there is a safe sequence and detect if there is a deadlock or not. So in this case, there was no deadlock. Alright, so now let's take another example. We'll be using the same processes and instances of resources and everything as the same here, but let's say that one of the process has now requested for an extra resource. Now let's see what happens and if there will be a deadlock or not when a process makes a new request for an instance of a resource. Okay, now let us suppose that process P2 makes one additional request for an instance of type C. So the request matrix is modified as follows. So this is the same table as before, but there is a change here now. P2 is making an additional request for an instance of type C. So P2, initially we saw that in the previous example that we took, P2's request was 000. It was not having any new request. But let's say that at some point of time, now P2 is requesting for one instance of C. So the new request of P2 is 001. So at this point of time, let us see if there will be a deadlock in this system. So let's apply our algorithm again and find if there is a safe sequence, or is it going to be stuck somewhere. So let's take the table again, which shows the available number of resource types at each instant of time. Okay, so we have the table here, and we see that currently our available instances of each resource type is 000. There is nothing available at the moment. Okay, now let's see which is the process that we can allow to execute first. So keep in mind that we don't have any number of resources available. So if you look at our table at the request column here, so P0 does not need any of the resources. So we can allow P0 to execute. All the other processes, they need at least one of the resource types. So we cannot allow any of them to execute because we don't have that many available resources. So only P0 can be allowed to execute. So let's say that we allowed P0 to execute. So P0 executes, and after P0 executes, it will release the allocation. That means whatever was held by P0 will be released. And what was held by P0, we can see here, nothing from A or C, but one instance of resource type B. So this will be released by P0. So now what will be the currently available? So the current available resources will now become 010 because P0 just released one instance of resource type B. So this is the available. Now let's see what is the next process that we can satisfy. Now P0 is complete. Let's look at P1. P1 needs 202. Do we have that much? No. It needs 2 instances of A and 2 of C, but we don't have. We don't have anything from A and C. So P1 cannot be satisfied. What about P2? P2 needs 0, 0, 1. It needs one instance of C. Do we have that? No, we don't have any instance of C. And P3, so P3 needs one instance of A. And do we have that? No, we don't have. We don't have any instance of A available. So P3 cannot be allowed to execute. What about P4? P4 needs 0, 0, 2. It needs two instances of C. And do we have that? No, we cannot execute. So we see that we don't have available resources for any of the remaining processes to execute. So they will end up waiting for each other and they will end up in a deadlock at this situation here. So we see that whatever order we try to follow, we are not able to satisfy the request of the other processes other than P0. So P1, P2, P3 and P4 will be involved in a deadlock because they are not able to get the available resources for their execution. So this is the time when we realize that a deadlock has been detected. So this is how, using our algorithm, we find that the deadlock is detected. So now that system is deadlocked. Although we can reclaim the resources held by process P0, the number of available resources is not sufficient to fulfill the request of the other processes. So that is what we just explained. Though P0 was allowed to execute and we reclaimed everything from P0, but still the number of available resources that we have is not sufficient for fulfilling any of the processes' request. So now we see that the system is in a deadlock. So this is how we can detect that a deadlock has occurred in a system where there are multiple instances of each resource types. So in the previous example that we took, there was no deadlock. There was a safe sequence that we could find. But here we see that there is no way to proceed and the system has come to a deadlock. So this is how we can detect deadlocks in systems where there are multiple instances of each resource types. So I hope this was clear to you. Thank you for watching and see you in the next one. In the previous lecture, we have discussed an algorithm for deadlock. Previous lectures we have been studying about deadlocks, and we have seen many ways for preventing deadlocks, for avoiding deadlocks and for detecting deadlocks. So let's say that now there is a deadlock that has occurred in a system. So how do we recover from that deadlock? So that is what we are going to study in this lecture. We are going to see how the operating system can recover from a deadlock once the deadlock has occurred. Alright, so what to do when a deadlock detection algorithm determines that a deadlock exists. So we have been studying about deadlock detection algorithms and we have seen how they are able to detect when a deadlock occurs. So once it detects that a deadlock occurs, what can it do? So here we are going to talk about two possibilities. So here the first possibility is inform the operator that a deadlock has occurred and let the operator deal with the deadlock manually. So here we are trying to just inform the operator that a deadlock has occurred and let the operator or the user take care of it manually. So we know that deadlock occurs when processes keeps waiting for each other and they form a chain or a cycle and they are not able to break off from that cycle. So when a deadlock occurs like that, we can inform the user that this thing has happened and let the user himself or herself try to eliminate some of the processes and try to deal with that deadlock however he or she wants. But this is not a good solution, of course, because not everyone is going to be able to know how to deal with these deadlocks. So this definitely is not a good solution. So what is the next solution that we have, or the next possibility that we have? So the next possibility is let the system recover from the deadlock automatically. So By automatically, we mean that the system should have some kind of methodology in itself using which it should be able to recover from the deadlock by itself. So that is what we are going to discuss in this lecture. What are the methods that a system can follow in order to recover from a deadlock once a deadlock has occurred? So here the question is how to break from the deadlock. So we know that deadlocks occur when processes are waiting for each other for some resources and then they form a cycle. We have seen that in the resource allocation graph. So how can we break from that deadlock? So here again we are going to talk about two options, and the first option is abort one or more processes to break the circular wait. So we know that there is a circular wait. That means the processes are waiting for each other and then nobody is able to release the process and nobody is able to get the process that they need because they are being held by other processes, and hence they form a circular wait. So the only way we can break off from a deadlock is by breaking that circular wait or that cycle. So in order to break that cycle, what we can do is we can abort one or more of the processes. That means we can terminate one or more processes so that when at least one or more processes break from that cycle, then we can assume that maybe that entire cycle will break and the deadlock will be resolved. So that is the first option that we have. And then the second option that we have is preempt some resources from one or more of the deadlocked processes. So again, let us recall how deadlocks happen. Deadlocks happen when processes are waiting for resources, but that resources are being held by another process. So that process ends up waiting for that other process. So what we can do, we can preempt some of the resources. So what do we mean by preempt? Preempt means we are taking back the resources from one of the process that is holding the resources. So for example, let's say that process P1 is waiting for some resources held by P2, and P2 in turn is waiting for some resources being held by process P3, and P3 is again waiting for some resources held by process P1. Now you see that there is a circle, there is a cycle that is formed, and there is a deadlock. So what we can do is we can preempt the resources from, let's say, P2. So P1 is waiting for P2. So whatever resources P2 is holding, we'll preempt, we'll take it away from P2 and we'll give it to P1 so that P1 at least can complete its execution and can break off from that cycle. So that is what we mean by preempting the resources in order to remove the deadlocks. So these are the two options we have in order to break the deadlock. So here in this lecture we are going to talk about this option 1, that is aborting one or more of the processes to break the circular wait. That means we are going to terminate the processes in order to break from that deadlock or recover from that deadlock. Alright, so let's talk more about this process termination. So when we talk about process termination, to eliminate deadlocks by aborting a process, we use one of the two methods. So again, we are going to talk about two methods using which we can terminate or abort the processes. So the first method is abort all deadlocked processes. So here what we are going to do is we are going to terminate all the processes that are involved in the deadlock. So let's take the previous example again. We said processes P1, P2 and P3 were involved in the deadlock. So what we are going to do is we will terminate all the processes P1, P2 and P3. So that is the first method that we have. That means aborting all the deadlocked processes. But here we see that it will break the deadlock cycle. For sure, the deadlock cycle will be broken by this process. That is sure. But it comes at a great expense. Why is that? The deadlock processes may have computed for a long time, and the results of these partial computations must be discarded and probably will have to be recomputed later. So why we say that this comes at a great expense is because there may be processes that have been executing from a long time. So these processes must have executed for a long time and must have completed a considerable amount of its execution. So by terminating it, it is going to completely lose all the execution that it has done till that point of time, and later it has to execute again from the beginning. So that much of time that the process took for its execution and that much of resources that it used will all go waste. So that is the great expense that we are talking about here. This is a costly solution. So the second method is abort one process at a time until the deadlock cycle is eliminated. So here, unlike the above method, we are going to just eliminate one process at a time and check if the deadlock is getting resolved or not. So we are not going to eliminate all the process at one go. What we are going to do is we are going to see what are the processes involved in the deadlock, and one by one we will terminate the processes. So for example, like let's again say P1, P2 and P3 are involved in deadlock, and now we will try to, let's say, eliminate process P1. We will terminate P1 and we will see after terminating P1 is the deadlock resolved or not, and if it is resolved, then well and good. And if it is not resolved, then we will try to eliminate or terminate one more process. Let's say we eliminated P2 and we check if now the deadlock is resolved or not. So in that way, we will keep eliminating one process at a time and check if the deadlock is getting resolved or not. So here let's see. Here it incurs considerable overhead, since after each process is aborted, a deadlock detection algorithm must be invoked to determine whether any processes are still deadlocked. So here I am saying that it incurs a considerable overhead. So why is that? This is because there is some time going to be spent in this method, because after eliminating a single process, the algorithm has to work. Which algorithm is that? The deadlock detection algorithm. So the deadlock detection algorithm has to work again to check if the deadlock is resolved or not. And if it is resolved, it is good. And if it is not resolved, we again eliminate, and after eliminating one more process, again the deadlock detection algorithm has to work and check if the deadlock is resolved or not, and so on and so forth. So this deadlock detection algorithm needs to work again and again, and hence it is going to cause a considerable overhead, or some time will be required in this method. So that is a disadvantage of this method. So it is not a costly solution as compared to this, because here we are not trying to eliminate the complete processes that we have. We are trying to eliminate one at a time, and we are trying to see if it is getting resolved or not. But it will take some time because of this overhead involved in running the deadlock detection algorithm again and again to check whether the deadlock is resolved or not. So these are the two methods that we have for terminating the processes. So we see that both these methods have their advantages as well as their disadvantages. But in both the methods, we see that we are trying to abort the processes. So now what about abortion of processes? Is it an easy task or is it a difficult one? Let's see. So here I say that aborting a process may not be easy. Aborting a process may not be an easy task. Why is that? Let's see. Let's see some examples why I am saying this. Here let's see one example. If the process was in the midst of updating a file, terminating it will leave that file in an incorrect state. So let's say that a process was involved in updating a file, and at that moment there was a deadlock that occurred, and hence we decided to terminate that process. So what happens if we terminate that process while the process was in the midst of updating the file? Then the file updation does not get completed. So the file will be in some incorrect state. Now here is another example. If the process was in the midst of printing data on a printer, the system must reset the printer to a correct state before printing the next job. So here again, let's say that a process was involved in using a printer. It was printing something using the printer, and in the midst of its execution, the process had to be terminated because of some deadlock that occurred. So what will happen? The printing will not get completed, and also when you try to do the next printing job, it may try to start from the previous job again. So in order to avoid that, we have to reset the printer to a correct state before it prints the next job again. So here we see again that this kind of problems can happen. So these are some examples just to show that aborting a process is not a very easy task. Now what if we use the second method that we discussed, that is not killing all the processes at the same time, but we are trying to partially eliminate the processes. That means one by one, if we try to eliminate the processes. Is that a good method, or is that also having some disadvantages? Let's see. So if the partial termination method is used, we must determine which deadlocked process or processes should be terminated. And this determination is a policy decision similar to CPU scheduling decisions. So as we already talked about, when we are going to terminate the processes one by one, there is a big decision that we have to take. That is, which is the process that we should terminate? Are we going to terminate any processes randomly and check whether the deadlock is resolved or not? Or is there a particular priority or some factors that we need to keep in mind while we are going to determine which process has to be eliminated? So this is also something that we have to keep in mind. So there could be so many factors involved. We cannot just randomly go and terminate the processes, which again may be an expensive solution. So we need to find out what is the best way to go about, what is the best order to go about in terminating the processes. So we should abort those processes whose termination will incur the minimum cost. So we should try to terminate the processes in such a way that the processes that will incur the minimum cost will be terminated, not those kind of processes that we took that example about, like a process that has already completed so much of its execution and was a big process and was almost going to complete, and at that time if we eliminate it, then that is a costly solution. That is not a very efficient way. So we need to decide what are the processes that we need to eliminate, what should we eliminate first, and then what is the order of priority in which we should go about. So this is one thing we should keep in mind. So there are many factors involved in this. So let's see some of those factors. So here we will discuss some of the factors that affect which process or processes are chosen to be aborted. So the first factor is what the priority of the process is. So what is the priority of the process? If we are going to eliminate a process of high priority, then that may not be a good idea. So we should try to eliminate or start eliminating processes of lower priority. So this is one thing we have to keep in mind, the priority of the process. And secondly, how long the process has computed and how much longer the process will compute before completing its designated task. So this is the thing that we have been just talking about. If there is a big process that has computed for a long time, and let's say that it needed just a few more seconds to complete, but at that moment there was a deadlock and we decided to terminate that process, then that is a very bad decision that we are making. Because if we just give a few more seconds for that process and eliminate some other process, then this big process can come out of the deadlock and complete its execution. And thirdly, how many and what type of resources the process has used. For example, whether the resources are simple to preempt. So this is another factor that we have to keep in mind. So how many resources the process is using and what are the type of resources that the process is using. So let's say that there are some processes that are holding resources that are difficult to be preempted. That means it is difficult to take that resources away from that process. So it may not be a good idea to terminate those processes. So again, the number of resources is also important. If a process is holding so many resources, will terminating that process be a good idea or not? So it may be holding so many resources and it may not be a very high priority process, and by terminating that process, many other processes that are waiting may be able to get the resources. So it may be a good idea to terminate that particular process. So in such a way, we'll have to see and make the correct decision. And fourthly, how many more resources the process needs in order to complete. So this is another factor. So if there is a process that is needing so many resources to complete, then it may be a good idea to terminate that, because anyway that process is going to again wait and again spend more time for its execution. So we can eliminate that or terminate that process. But if there is a process that just needs, let's say, one more resource to complete its execution, so we can terminate some other process that is holding that resource and give it to this process so that it will get that one resource, complete its execution, and then it will be able to release all its resources again. So in that way, we need to see how many more resources the processes will need for its completion. So this is another factor. So coming to the fifth one, how many processes will need to be terminated. So this is also very important. We don't want to just randomly terminate as many processes as we need. So we need to follow some order in which we will have to terminate the minimum number of processes. So when there is a deadlock, we want to terminate only as many processes that will lead to breaking of the deadlock. We don't want to eliminate so many processes. So by eliminating the minimum number of processes, we need to come out of the deadlock. So we need to find what is the order, what is the priority, and what are the other factors involved in order to achieve this. Now coming to the last one, we have to check whether the process is interactive or batch. So interactive process means a process that requires user interaction. So it may require some input from the user or something like that. From the name itself, it is evident. So we have to check if the process is interactive or a batch process. Batch process means it is running some bulk job. There is a bulk job that it is trying to achieve. It is trying to run and finish some bulk job. So we need to again see where is the weightage that we need to give here. Should we give priority to interactive processes or to the batch processes? And we have to decide which is the process that needs to be aborted. So these are some of the factors that affect which processes are chosen to be aborted. So this may not be the complete list. There may be even other factors that the OS has to keep in mind while deciding which are the process or processes that are chosen to be terminated. So taking into consideration of all these things, it has to come up with the best solution or the best way in order to eliminate the minimum number of processes in order to come out of the deadlock. So this is what we have to do in case of the second method, that is eliminating one process at a time. So here we see that there are a lot of computation work going on. There are so many factors to be kept in mind, and it may involve some time. So that is the overhead that we were talking about. But the advantage is that we are not eliminating the entire processes. We are trying to eliminate as minimum as possible. But in the other method that we discussed first, it is just going to eliminate all the processes at one go. So the advantage of that method is the deadlock will be broken. The system will recover from the deadlock at that time itself for sure. But it is a very costly or expensive solution, and we have discussed why is that. Alright, so this is the first method of dealing with deadlock, that is by process termination. And in the next lecture, we will be discussing the next method, that is by preempting the resources from the processes. So I hope this method of recovering from deadlock was clear to you. Thank you for watching, and see you in the next one. And they are not able to we have discussed about one of the methods of recovery from deadlock, which was process termination. And in this lecture, we are going to discuss the second method, which is resource preemption. So we will see how we can recover from deadlock using this resource preemption method. So here what we do is, we successively preempt some resources from processes and give these resources to other processes until the deadlock cycle is broken. So in the previous method, we have seen that when a deadlock occurs, what we were doing is we were just terminating the processes. But here we are not going to terminate the process, but what we are going to do is we are going to take the resources from some process and give it to another process and try to resolve the deadlock. So we know that deadlock happens when processes are competing for resources which are being held by some other processes, and hence they end up waiting for each other. So if we can take the resources from some processes and give it to some other processes that are needing that resources, and we can allow at least some of the processes to complete their execution and hence come out of the deadlock. So that is what we are trying to do here. Now, if preemption is required to deal with deadlocks, then three issues need to be addressed. So if we are going to deal with deadlocks using the preemption of resources method, then we need to address some of the issues. Like in the process termination method, we discussed about many of the factors that we need to address. So similarly here, there are some issues that we need to address, and they are selecting a victim, rollback, and starvation. So these are the three issues that we need to address if we are going to make use of the resource preemption method for recovery from deadlock. So we will be seeing these issues one by one and try to understand what this is and why it has to be addressed. So let's start with the first one. So the first one is selecting a victim. So what do we mean by selecting a victim? So here it means which resources and which processes are to be preempted. So we have already said we are going to preempt the resources. That means we are going to take the resources away from the processes. So which are the processes from which we are going to take the resources, and which are the resources that we are going to take away? So those processes from which the resources are going to be preempted, they are known as the victims. So we need to select which processes are the victims, and we need to determine the order of preemption to minimize the cost. So why do we say this? So when we select a victim, we need to see which is the best possible candidate for this. Because if we choose some processes that already has completed a lot of its execution and was needing just a few more resources, or if it was just needing a few more amount of time to complete its execution, and if we take away the resources from that particular process, it may not be a good idea. That may not be a very efficient solution. So we need to choose which is the process that we are going to preempt the resources from. So here we are saying that we need to determine the order of the preemption to minimize the cost. So what do we mean by the cost here? So by cost, we mean parameters such as the number of resources a deadlock process is holding and the amount of time the process has thus far consumed during its execution. So this is what I just explained. We need to take these factors into consideration when we choose the victim. So keeping these parameters in mind, we need to make the best decision of choosing a victim. So that is what we mean by this issue of selecting a victim. Alright, so now let's go to the second one. So the second one is rollback. So what do we mean by this? What should be done with the process if we preempt its resources? It cannot continue its normal execution as it's missing some or all of its needed resources. So once we decide a victim, that means once we select the process for preempting its resources, what do we do with that process after that? What do we do with that process after we preempt or take away the resources from it? Definitely it cannot continue its normal execution because we have taken away its resources. So it may be missing one or more of its resources, or it may even be missing all of its resources that it needs. So what do we do with this? So for this kind of processes, we must roll back the process to some safe state and restart it from that state. So we know that when a process executes, it starts and then it goes up to the end of its execution. So before it reaches the end, if we are preempting its resources, then it would be stuck in some middle state. So in that cases, we have to roll back that process to some state before, which is a safe state. And then later on, when the process will be able to get the resources back, it should restart its execution from that particular state. So that is what we mean by a rollback. We are taking the process from the point where its resources got preempted to some state before, which is a safe state. But what is a safe state? So how do we determine if the previous state was a safe state or not? So it is difficult to determine what a safe state is. So the simplest solution is a total rollback, which means abort the process and then restart it. So here it is difficult to determine what is a safe state because it will require a lot of computation and application of some algorithms again to find out if the previous state was a safe state or not. So when we are rolling it back, we are taking that process back to some previous state and we have to check whether that state is a safe state or not. And if that is not a safe state, we have to roll it back again. So we have to always check if that previous state was a safe state or not, which requires a lot of computation and it is not very easy to do that. So as it is difficult to determine what a safe state is, the simplest solution that we have is a total rollback. So total rollback means we are rolling back the process to its initial state. It is equal to terminating the process. It is just like we abort the process and then we restart it. So this is almost becoming like terminating the process. So this may not be the best solution. It may be the simplest solution, but it may not be the best solution. So this is what we need to remember in rollback. So when we roll back, if we can roll it back to a previous state which is safe and we can assure that there is a safe state, that is the best thing to do. But if it is difficult, the simplest thing to do is total rollback. But that is equal to aborting the process and restarting it. So this is another issue that we have to address, that is rollback. Alright, so now let's go to the third and the last one. So the last one is starvation. So how do we ensure that starvation will not occur? And how can we guarantee that resources will not be preempted from the same processes? So we know what is starvation. Starvation is when a process is waiting for resources and it just keeps on waiting and it never gets the resources. So it is starving for the resource and it never is able to complete its execution. So that's what we mean by starvation. So in this resource preemption method of recovering from deadlocks, if we are selecting a victim and if we just keep on selecting the same victim again and again, that means if we are just selecting the same process again and again, and from that same process the resources are preempted, then that particular process will end up starving for resources. So if victim selection is primarily based on cost factors, it may happen that the same process is always picked as a victim. As a result, this process never completes its designated task. So if we are selecting the victim based on the cost factors, so we have discussed some of the cost factors. So according to the algorithm, applying all the cost factors, it may just select the same victim again and again. So let's say that there are a few processes and there is one process which is not of very high priority and also it is not holding so many resources. So according to the algorithm that is trying to select the victim, it finds that that particular process is the best candidate. Let's make that process a victim because anyway it is not of high priority and also it is not holding too many resources. So let us select that process and take away the resources from it. So because of these cost factors, that same process could be selected again and again by the algorithm. So that process will end up in starvation and that process will never be able to complete its task. So how can we avoid this? So we must ensure that a process can be picked as a victim only a small finite number of times. That means we should have a particular count or a limit and we should say that a process should be picked as a victim only that many number of times. We should not allow a process to be picked as a victim again and again. So the best solution for this is include the number of rollbacks in the cost factor. So the number of rollbacks. So when a process is picked as a victim, that means we are going to preempt its resources. And when the resources are preempted, what happens? We discussed in the previous point that it should be rolled back to some safe state. So whenever a rollback happens, that means that process was chosen as a victim. So if there are too many number of rollbacks, that means that process is being chosen again and again as a victim. So we should include the number of rollbacks in the cost factor. So this also should be one of the cost factors that will decide which is the process that is going to be picked as the victim for resources preemption. So these are the three issues that we need to address if we are going to make use of the resource preemption method for recovering from deadlock. So the issues were selecting the victim, rollback and starvation. So I hope this was clear to you. So with this we have come to the end of the chapter of deadlocks, and here we have seen many things like what are deadlocks, how do deadlocks occur, how can we avoid deadlocks, how can we prevent deadlocks, how can we detect deadlocks, and how we can recover from deadlocks. So I hope this chapter was clear to you, and so in the next lecture we will be taking some problems or questions asked on deadlocks and we will see how we can solve them. So I hope this was clear to you. Thank you for watching and see you in the next one.